Now, how do we solve, how do we use algebraic method? For algebraic method, the usual procedure, so algebraic method, the usual procedure is from the line, solve for one of the variables, preferably y, then substitute in the original. So, in the other. So, for instance, from the linear, just say line, we solve for y. Y is 1 minus 2x over 5. Then substitute that in the equation of the quadratic. This is y, 1 minus 2x over 5. And that is equal to 3x squared plus 7x minus 49. So will you simplify that in your seats? And tell me what the simplified form is. Write it in the form ax squared plus bx plus c. To be able to solve for equals 0. Come on. Okay. So, we're now here in number 3, solving the system of equations. There are really two types of solving equations. One is when they are both linear, and in our example here, one is quadratic and the other is linear. So what we do here is from the linear equation, you have 2x plus 5y equal to 1. But we know that y is equal to 3x squared plus 7x minus 49. So instead of y, this y here, we put that in, we plug it in. So 2x, this is 2x, 5. Instead of y, we put this in. So you have 3x squared plus 7x minus 49 equal to 1. So we have it here. So simplifying, 5 times 3x squared is 15x squared. And then, what is this? 5 times 7x, what's that? 35x plus 2x, that will give us 37x. So when we write that, that is 37x. And then, 5 times negative 49, what is it equal to? 245. That is minus 245. It's equal to 1. But we want it in the form ax squared plus bx plus c equal to 0. All the time, the right side should be 0 if we have to solve for x. So we transpose that 1 over there. What do we get? We add 1, minus 1. When we transpose, that becomes minus 1. So then we get 15x squared plus 37x minus 246. So, quadratic formula or factoring. For quadratic formula, that's really very mechanical. You don't have to think, no? So, let's use quadratic formula. The quadratic formula is, we write it again, or let's just point it out. X is equal to, first of all, you must have this long fractional line. Some of you just put the fractional line beneath the radical. Kasama this should be included. Kasama dapat ang minus b. So, minus b plus or minus the square root of b squared minus 4ac all over 2a. Now, we put it here. What is a? This is now our equation. So, what is a? A is 15. And what is b? 37. And what is c? Negative 246. So, x now will be minus b minus 37 plus or minus the square root of b square, 37 square, use your calculators, minus 4, a, which is 15, c, which is negative 246, all over 2a. 2 times 15 is 30. So, what are the values? Use your calculators. What is 37 square? 1360.
1363.
13. So will you add this and then get the square root? Minus minus becomes plus. That's why you have to add. 4 times 15 is 60. So 36 carry 20. Sandali. 6 times 6, 36. Carry 3. 7 ito. Tapos 1, 3, 6, 9. Add. Well, anyway, square root. 127. Exact. 127. So, 130 minus 37 plus or minus 127 all over 30. So, what are the roots? 3 at saka negative 82 over 5. When you have the negative 37, negative 127 will give you negative 14 carry 1, 164. 164 divided by 30. So 164 divided by 2 will give you what? Negative 82 over 15. So Eileen is correct. Thank you, Eileen. So we have 2x plus 5y is equal to 1. So when x is minus 82 over 15, minus 164 over 15 plus 5y. So being for y, 1/5, 1 plus 164 over 15. So 15 plus 164, 179. So that is the intersection. Okay. So now we go to, after we finish number 2, topics that we should know about the divine proportion, then we consider your questions if you have any questions. Another item for review, which I did not include here, will be the operations of functions, addition of function, the resulting function, plus, f plus g, f minus g, f divided by g, f of g, g of f. Review that, no? Or if you like, later we'll include that. So, thank you, Carlo. I will take up. Gininto ang parihaba at malajos ang proportion. So, the translation there is, gininto ang parihaba means golden rectangle, and malajosa means divine proportion. The golden rectangle has been known many centuries BC, no? And during the Greeks, the Greek period, I mean, the golden age of mathematics in the Greek period. They are our mathematical fathers, okay? They studied about the divine proportion. What is it? For instance, when they are not racist, no? The Greeks, when they do beauty contests, it doesn't matter if you are white or if you are short or if you are pango, if you are flat nose, pug nose. What's important is in the proportion. And they started with a line. They say that the most divine or the most beautiful way of dividing a line, as you know, the Greeks really incorporated mathematics, religion, arts, in their politics, in their lives. So, they say that for a line, suppose that this is your line, and you want to divide this in the most beautiful way. And if you look at your body parts, you have really lines. You have from here to your elbow, from your elbow to your fingertips, and so on. Here, and your eyes, etc. And everything is in divine proportion. I mean, very close to divine proportion. Sometimes it's not close, but Kaya nga, babawi. No? So we can... sometimes a baby knows if you are in divine proportion. Have you ever seen someone, or have you ever been in front of a baby and looking at you, he cried, humagulgol, or naimpatso? Because the baby knows how to look at divine proportion. Maybe you are not so divine in the baby's in the baby's sight. Or sometimes, just by the looks of a person for a baby, the baby is very happy, very pleased to see you. You are in divine proportion. That's why in our, one time, in the Institute of Mathematics, a teacher brought his daughter in the office, and he was really good looking, the assistant. And when he came, the baby was excited. She wanted to play with the guy and so on. And then, come, let's see, we measure you must be in divine proportion. And indeed, everything in his face is, and even in his height, is in divine proportion. Very, very close to 1.62. So, well, at any rate, what did the Greeks say about that? Suppose that you divide, meaning that half-half is not really beautiful, no? You are not really symmetric. Even looking at your face, the other half is not exactly equal to the same as the other face. Sometimes it's more puffy here because this is where you always chew and there's no more teeth here and so on. So, well, anyway, so suppose that the longer length is A and the shorter length is B. And the Greeks say that the most divine way, or the most beautiful way of dividing a line segment is such that the ratio of the smaller to the longer to the smaller is equal to the ratio of the entire is to the longer. Now, what is that proportion equal to? That is equal to phi. Now, so how do we do that? By using golden. How did the golden rectangle come in? Nagmamakinilya. Okay. So I'll say this in English. It's important to the Greeks. Mahalaga sa mga Grego ang geometria. Geometry is important to the Greeks. Geometry ang Euclidean geometry, na siyang tungkol sa pagsusukat ng bagay-bagay sa ating kapaligiran. It's about the measurement of things in our surroundings. Because, why? We are interested in our surroundings, but there is also beyond, no? And so the geometry is not only in our immediate surroundings, but the Euclidean geometry is in our immediate surroundings. Like, for instance, if you see a railroad, or the road, or railroad, the rails should not really meet, no? But at a distance, they seem to meet. Or if you, in the fields, the tilapil, the squares there, you see the squares, then they sort of converge, no? But they are supposed to be parallel. They're supposed to be rectangular. So the fields are divided into rectangles so that the water will be contained. So many rectangles. But when you see them in a distance, it looks like they intersect at a distance. So there is a measurement in the immediate surroundings, and Euclidean geometry takes care of that, and also beyond. And one of them beyond is, so the artists told the mathematician, you say that parallel lines do not meet. How come? Look at the rails.